Included with your TPS method on the MP1 are these items. This is your sample lid used for if you notice any thermal drift in your test data. Again, it's not typically used, but if you notice that your room has drift or your environment has temperature drift, you can use it to protect your data in your sample. Max temperature for this is 60 Celsius. There are other options if you want to cover your sample up to a higher temperatures, but make sure you don't use this above 60 Celsius. This is the sample adapter, sensor adapter rather. This allows you to mechanically affix the TPS sensor to the adapter and on the sample holder. Max temperature for this adapter is 60 Celsius. We do have a 300-degree version of it if it's needed. The sensor that is included with your basic TPS package is 33171. This is 6.4 millimeters radius. The sensors that are included, they can be used up to 300 Celsius, but remember, you always have to upgrade your adapter if you're going to go above 60 C, even if the sensor can. Your sample holder, which the adapter is used to configure your samples with the TPS sensors. It can go up to 300 Celsius, but remember that you have to upgrade your adapter and your lid if you want to use these two in combination. This is the included foam used for testing single-sided or asymmetric configuration. Stainless steel verification samples, which you can use to verify your system's operation or training. A protection stainless steel just goes on top of your sample for protecting your sample from clamping force. That's what's included. In this section, we'll be discussing sample setup. So for connecting your sensor to your adapter, before I put it together on the sample holder, I'll just demonstrate how to do that to give you a little bit better view. So your sensors come in a protection sleeve. When you're not using them, put them back and that'll keep them safe. So to remove the sensor, you just open it up and withdraw the sensor. You'll notice your sensor has 4 contacts. These contacts need to be made with contacts that are inside the adapter to make measurements. So to get a little closer, you can see that the adapter has a cutaway that allows you to see when you've properly inserted the sensor. So although I'm going to show this on the sample holder, I thought it would be good to show close up. So putting contacts down, we're going to slide the sensor into the opening. And if I turn it up, you can see as the sensor covers the 2 exposed contacts in the back. And then by turning it flat so it doesn't fall out, again, that shows you that you've created contact to sensor mechanical contact. And then by turning the upper plate down with this set screw, it closes the contacts on the sensor and you've made good contact. Now, from here, we could simply insert the adapter on the sample holder, but that tends to not be the norm. Typically, you're changing sensors with it on the sample holder, which is what I'll do just to make this as close to real use as possible. So let's cover hooking the adapter up to the sample holder. There's a square cutaway and there's a square pole. We're going to set this up with the adapter facing the inside of the sample holder. So by placing that over the square hole and making sure it slides, there's a screw here that we're going to make sure that's backed off. And now that can move up and down. And this is how we adjust for sample height. The thicker your sampler is, the higher that sensor has to be, which is by moving that up and down you can accommodate. So, and then once you're in place of desire, you can set that screw and that affixes the adapter. So we'll adjust that to the samples we're going to test shortly. So again, as I demonstrated, we're going to insert the sensor into the opening with the contacts down. If you want a close-up of this, just rewind the video. Again, I'm inserting this until I see the back side of that sensor, and then affixing the mechanical contact. If you forget to do this and you try to measure the resistance of the sensor, it'll show as a high resistance. First thing you can check as soon as you do that, make sure that's affixed. How tight does that need to be? Just thumb tight, which is typically when you feel resistance on the sensor, just 1/8 of a turn is plenty. And then we'll adjust the height based off the sample configuration. So for adjusting the upper portion of the sample holder, it has two adjustments. One, if you want to think of it as macro change, we can do up and down by pulling, which are spring-loaded knurled knobs on the side, and they lock into positions so that when you turn the screw down, this top bar doesn't move any further. So for large adjustments, we use the bar, and for fine adjustments, we use the knurled knob on top. So we're going to demonstrate our stainless steel materials as part of the training. So I'm going to put one on the bottom. And lower the adapter until the sensor 6 sits relaxed. What I mean by that is there's no major angles up or down. It's sitting relaxed. And you can adjust that. Again, that should be affixed. The sensors are fixed. And I'll put the top on. It is very important to use, especially if you're testing these verification materials, because we want to maintain good surfaces, to use your protection piece of metal on top. And of course, you would use this in your sample as well. And by backing off the screw the majority of the way, we can set the top bar to be as close as possible to the top of the two-sided setup. So what we refer to this is the symmetric or the two-sided setup. Again, you only need finger tight. So finger tight, as soon as you feel resistance, an eighth or a quarter turn is plenty. And if you have doubt, if you just use your finger and push that top sample, it should not move. And what that's doing is bringing the two sample halves together to create intimate contact with the sensor. I'll take this apart and show you the asymmetric configuration. So if we wanted to do asymmetric configuration, we would use these two samples. So included in the software are the thermal conductivity and thermal diffusivity values for both of these, but if you ever wanted to verify what is being used as the known backing, you could measure this as a set. But typically you only need one piece. This fits on the bottom like that. Again, we would lower the sensor adapter to where the sensor is sitting flat. And now we have a asymmetric setup. So we'll introduce only one half of the sample, or one piece, onto the sensor. And again, you want to make sure that your sensor is sitting as best as visually possible in the center of your sample. The samples don't have to be round. They can be square. They can be various shapes. So within the greatest radial distance in any sample surface, you just want that sensor sitting in the middle. So repeat the process where we lower it, and we just turn the knurled knob until we feel a little bit of tension, and then an eighth or a quarter turn is plenty. So that's the asymmetric setup and the symmetric setup for measuring stainless steel. This is on the bench for room temperature. If we had a high temperature version of this, meaning a high temperature adapter, we would insert this in an oven. Again, this can go up to 60 Celsius as it is right now. So you could in fact put this in an oven, and with a porthole, you would run this through the porthole and connect it to your system. And that would allow you to make measurements in an external chamber up to 60 C. Included inside this adapter is a temperature sensor. So along with measuring conductivity, we're actually reading the room temperature of the area near the sensor. So recording thermal conductivity, the raw data, and thermal diffusivity, as well as the temperature. And that's the sample setup. Oh, if we had possibility of drift, again, it's not very often we have to use this, but if you do see drift in your sample, and there's no downside to using it, so if you want to use it, you certainly can. That's how the sample lid is used. The last step of setting up your sample holder for the TPS method is connecting the LEMO connector to the controller. So bringing this close to the camera to describe a couple features of this LEMO connector. The red dot is top center, and there's barbs that connect, that hold the connector to the controller. When you're inserting this, those barbs auto lock, but when you want to remove the LEMO connector, you have to pull back. You can do this with one hand, but demonstrating it here, you can pull back on the sleeve. You can see the barbs release. And that's what enables you to remove the connector from the controller. So we're going to align this red dot with a red dot that is top center of that connector end. And we're going to bring the camera a little closer to show you that. You might not be able to see the red dot as easily, but there is a keyed section, so you can only put it in one direction. And you'll feel it click, and then that's affixed. So to remove it, this is probably the more important section, you just simply hold this portion of the adapter and pull. You should not yank on the cable. This is not how you release it. You pull this section. Of course, you can just do it overhand, but you won't be able to see it. Remove it. So once that's connected, then you're ready to proceed with your software step. In this section of the TPS training, we're going to discuss how to make a measurement software-based. So by double-clicking on data acquisition, we've already covered software installation and the commissioning setup. So once your data acquisition is started, and again, this portion of the software or the application is used for running the controller and collecting data. We can go to this section in the hardware configuration, and we can load current devices. So from the previous installation, commission setup, we detected this controller. Now it auto detects the plugged in adapter, sensor adapter, and it tells you that there's a room temperature sensor adapter. If you have other accessories, you would repeat this process for those, such as a high temperature adapter or temperature platform or other methods. This is where you would load those, and they would become part of your permanent profile. So we can load the current devices. Successful. Let's save that change. So when we go to our home, our current profile, which is our permanent profile, shows the controller as well as the adapter that we're going to use for testing. So for making a measurement, we go to this icon, and these are the fields that are the first portion of the general tab. The required field is your name, so you would put in the user's name. All the rest of this is just for your own records. And going to the right side of the general tab, which is where we'd pick the method we're going to use. So in this case, this system was purchased in the TPS method, transient plane source. So we're going to select 3D disk source, transient plane source. This gives us a number of options based off of, again, what modules are included with your system. And if you want to review that, you can go to About. So in the About section, it shows which methods and which modules are included in your system. So if you're missing any, or if you want to add other modules, and those modules, what they are and how they're used are covered in future training. They're listed here and can be added at any time. So in our case, we have a full access to all the modules, but the ones that are included in the basic system, so the MP1 with TPS method basic, are 3D disk source, symmetric, which is two-sided, asymmetric, which is single-sided, and isotropic. The anisotropic and slab are other additional modules that you can add to the system. So we want to direct the software where we want the data saved. So we're going to just put this on our desktop for now. And we're going to select symmetric because that's what our current configuration of the stainless steel is. We're going to select isotropic because our samples are considered homogeneous and isotropic. And we're going to click Next. In this Devices tab, it auto-detects the controller. Again, that's part of your profile, as well as the device your sample is currently set up in. And if you recall, this controller has 4 ports. The port on the front of the controller is port 1. So that the current adapter that's connected to that is a room temperature adapter. That's why it's referred to as a room temperature device. If you had additional devices connected to it, they would be in this list. Here, we can add the name of the sample. So we're going to add stainless steel. The volumetric heat capacitance of the sample is not required, but if you want to enter it there, if it's known. The sample height, so with calipers, you can measure your height. For these samples, they are 20 millimeters tall or high, and they are 20 millimeters radius. Any sample notes you want to include, these notes are included in your exported data. You can record them now. Sensor port, again, if you have multiple devices connected to this, they would show up in this list. We only have one room temperature TPS sample holder, which is on port 1. So we're going to select that. The sensor model, that is the number that is labeled on the side of your sensor. The current sensor we have listed, or rather connected to our adapter, is 33171, which is 6.4 millimeters radius and polyimide or capped on insulated. This step is really quite key, and this allows the user, before you proceed with measurements, to check the resistance of the sensor to make sure they've made connection between the sensor and the sensor adapter. So the system will actually probe and do a quick resistance check to verify that resistance is made. It will actually do a passive confirmation that the resistance that it records is reasonable for the sensor that you have selected. If you've selected the wrong sensor, it will actually warn you that the resistance is not valid or not ideal for that sensor. Your adapter, if you recall, has a built-in sensor, temperature sensor, so you don't have to include a sensor, or rather a temperature of your sensor. If you wanted to manually do that, you could put it here. But of course, we want to automate as much as possible. Test time, this is these variables are key to making good measurements, blah, blah, blah. Okay. In the sample tab, there are a number of fields that are required. Here we can name our sample. If you happen to know the volumetric specific key to your sample, you can input it here, but it is not required. These two fields, sample height, or how tall your sample is, and sample radius, which are used to calculate the available penetration depth. And what that is the distance from the edge of your sensor to the edge of your sample. If whatever number you put in here, the software will auto-calculate what the penetration depth is from the measurement based off the diffusivity of your sample to ensure that the heat from your sensor never penetrates past the available boundaries. That's quite key. So this sample is 20 millimeters tall and 20 millimeters radius. Sensor port, again, if you recall, each controller for the MP1 has 4 ports. Port 1 is again on the front of the instrument, and that's where our room temperature sample holder and adapter are connected. Itself recognizes that. There's an identifying chip inside the adapter, so it knows which port it is connected. The sensor size selection, so on the sensor itself, on the TPS sensor, there's a model number in white, and that corresponds to the model number in the software. The sensor that comes standard with the TPS package for the MP1 is 6.4 millimeters radius in polyimide, and the model number is 33171. As you can see, there's a range of other diameters that you can select. We will certainly discuss more about sensor selection shortly, but ideally, with the basic package and the verification sample, you can always use 3371. At this point, we're going to check the resistance. What that means is that this instrument allows you to verify the connection between the sensor and the adapter. That's been made correctly. And it's a critical step to save time, because if you set up a schedule and the sensor's not made correctly, a bunch of time would be wasted in setting up that profile. So this is a quick verification of resistance. So it goes out and measures the resistance of what's connected in that sensor, and based off of your selected sensor model, it verifies there is an acceptable resistance based off of that particular diameter of sensor. So it checks two things. It checks that the sensor you have selected is correct, as well as it has a matching resistance. The temperature of the environment that your sample and sensor adapter are sitting are auto measured If for some reason you want to input your own temperature, you can turn off that auto read and input it manually. Typically, we just leave that on. So both the room temperature adapter as well as the high temperature adapter record the temperature of its environment. Test time and power. So here's the really critical portion of selection of parameters. There are a number of resources that we have that you can review in addition to this. Today we'll just talk about what the requirements are and proceed with testing and allow other resources to dig deeper into those. So selection of sensor. We initially configured this sample for 33171, which is 6.4 millimeters radius. But for selection of sensor, typically you want your sample to be twice the diameter of your sensor. So there's a number of sensors that all the way from 1 millimeter diameter all the way up to 60 millimeters diameter. So typically we want to select the largest sensor we can that meets that requirement, that our sample is twice the diameter of the sensor. Again, sample does not have to be round or square or any other dimension or specific dimension for that matter, but the available area or radial penetration area should be twice the diameter. Test time. Test time, we want to select a test time that penetrates into the material. And how do we know that? It's because the system measures thermal diffusivity. So we want to penetrate into the sample from any edge of the sensor equal to the radius of that selected sensor. So there are other resources, again, that dig a little further into this. To assist with that, there is what's called a total to characteristic time, or TCT. And that range, which will be up on the screen, 0.3 represents the radius of the selected sensor. So by selecting 6.4 millimeters radius, this measurement that I'm going to make, it will ideally look for a penetration depth of 6.4 millimeters penetration or greater, but not over penetrating the available dimensions of the sample. So that's test time. Power serves to make sure that we're getting a nice clean signal. That results in a temperature rise within the transient. We want that transient to meet a minimum temperature rise. The maximum temperature rise is dependent on the material and the power used, but as long as we achieve a minimum temperature rise, our transients should be free of noise. There's a wide variety of power. Of course, the selection of power depends on the material you're measuring. So in this case, we're going to do 5 seconds with 1,000 milliwatts. So this quick transient function, this allows us to vary the parameters within the sample tab to determine what parameters we should use. So it's a quick measurement or allows a quick iteration of measurements to verify we have the right parameters. Of course, we don't want to rely on this function to record our final data. We want to use the schedule to do that, because that's where you get the opportunity to make sure you're following good practices on allowing the temperature you introduce into the material to dissipate between measurements, as well as the convenience of the schedule and maximizing the available switches. That's where you gain the convenience of that. But in this case, we'll certainly show a quick transient. A quick transient update window shows up with the event log. The event log gives you a play-by-play or time-based set of steps that the controller is doing as part of what you've asked it to do based off of test time and power. When a typical measurement is made in the schedule, the system records drift, which is in advance of every measurement, a 40-second measurement of just the temperature at the interface between the sensor and the sample. That's the drift recording, and then it makes a series of transient measurements based off the parameters you set up in the schedule. But in the quick transient test, we don't record the drift, because this is meant just as a verification of your parameters. So it's running test 1 that we requested, which was 5 seconds at 1,000 milliwatts. You can see it's done. It's rather complete its measurement and analyzing. This is our transients. So you can see from our transient curve. So we verified that. And if we go to the results tab, it will give us a number of other pieces of data. So here is your conductivity and diffusivity. But more important we've met the temperature rise requirement, so 0.8 degrees. we've met the minimum total to characteristic time of 0.3. So the actual characteristic time measured for this sample is 0.46. Again, that represents the penetration depth of the measurement. So the sensor selected is 6.4 millimeters radius, in this case, 33171 sensor. It has a radius of 6.4 millimeters, and we've penetrated beyond that minimum, which is 8.7 millimeters of penetration depth. So this is certainly acceptable test time for this verification material. So we can close, and we can click next into the schedule to allow us to set up a schedule of measurements. So there's a number of ways of making measurements within the schedule. The simplest is just add one item. So it allows you to select a number of measurements with a delay and the test time and the power you selected. There's certainly a lot of diversity you can enable here, which we'll cover in a separate section. If you click stabilization, this allows you the most basic function to add a 10-minute delay between the quick start, the quick test, and the first measurement of the series. We're going to enable that. We're going to leave the drift recording on all the time, so that way if there is any change in the environment temperature-wise, or if you've brought your sample from the outside to the inside, where there's a delta T between those two environments, it will be recorded. Why is that important? Because your results may be affected by that drift. And then we can proceed with start test. And here is our window, or a display window of our measurement series. So as you go through and add more schedules, depending on the channel and the work, the right side of your experiment list will grow in sequence. And we'll cover that in another section as well. But the current measurement request or schedule is 5 tests at 5 seconds and 1,000 milliwatts with a stabilization period of 10 minutes. So as you can see from the event log, the current waiting period is 10 minutes, which is counting down. So in this section, we'll fast forward through this a bit, but allow this to be shown in its entirety in this training video. And at the end, we'll just sum it up and continue on with further training. Now that the measurements are done, we can review the data by clicking on individual experiments. So in the event log, it records each test within the schedule, so you can review individually. And again, this is where you informally look at the results. So here you can see tabs of the raw data and the residuals of each. Or you can open this data in the transient analysis module. And we'll talk about the transient analysis module in the second section of this training. Now that our schedule is complete, we can open up the transient analysis for reviewing the results. So to open up the transient analysis application, we double click on the icon. And this part of the application is specifically used for reviewing results. There's quite a bit of sophistication in this application that allows you to open up multi-types of experiments and analyze them in a variety of ways. In this case, we'll look at the basic function. Certainly other resources are available for digging in and looking at the full capability of the analysis application. So we can open up data from Open File. Here is the test data from the schedule we ran on our symmetric measurements of stainless steel. It also records the quick transient that was done as part of the parameter optimization, but we want to focus our calculations on the scheduled data because that represents the data that has stability, drift recorded, as well as the time delay or stability delay between each experiment. So it represents the best repeatability capability of the instrument. So on the left-hand side, we have the parameters that were used in each column, seconds and power. This is the recorded room temperature or the environment temperature. This is the sensor that was used as well as the radius. There are a number of other columns that you can display. By right-clicking in this header, you can show different columns, the ID, the dates, etc. We're going to leave it in default. So when you select one or various by Shift Select All, you can see your transients of temperature rise versus time. So again, this is the heat from the sensor diffusing into the sample, and this is a recording of the change in resistance with time. So in this case, our 5 seconds. And with 1 watt or 1,000 milliwatts, we've produced just over 0.8 degrees Celsius temperature rise. So that's our raw data. We want to remove this portion of time that represents the contact resistance between the sensor and sample. And we'll talk about that when we get to the calculation part of the measurement. The next tab is the drift. So we want this drift to be random. And if we individually select an experiment, it shows the drift recording for that particular experiment. Or we can select all of them and see that the drift is random for all the experiments. If there's any behavior in the drift, meaning a downward slope or an upward slope, there'll be a line recording that trend, which will warn the user that in fact that sample has drift, and you might want to consider remeasuring it or apply a drift correction. This is the results that we're going to calculate, showing the change in temperature, and of course these are all within a tight time frame of room temperature. If your temperature range was very wide, meaning other temperature ranges, you would see this plotting all that. But you can see that the conductivities are all very similar. This is the residual. So this means from the portion of the line that we've calculated, this is the fitting quality. And this is a key part of the determining that we have good measurements. And our bulk results are the last tab. So this is a summary of the results of that sample. So if we select one or all, it shows all the data. So this is default calculated within a specific set of applied parameters that most likely is going to be beneficial, or rather sufficient for all the experiments you might do. But if you want to go in and edit that specific calculation, this is where you click Edit Calculation, and that allows you to edit some of the default or add particular variables to experiment and see the effects of those. So you can edit an experiment, or you can add a new experiment and vary those parameters that way. So let's say you wanted to manually remove the contact resistance between the sensor and sample by clicking contact resistance. And what this does this calculation modifier, it allows you, it uses the data from time 0 as the heat penetrates through the layer of resistance that's between the sensor and sample. It calculates that contact resistance. So because that is a known contact resistance, you don't have to manually remove that portion of time. That's automatic. So default, we want that used the majority of times. It's an advantage to do that. But if for some reason you want to calculate in a manual way, you can add another experiment, another calculation that is, and you'll see another calculation window show. So your default experiment is there. You can review the data as well as the data from the other calculation window. So you can add a number of experiments and see the effects of those. And then you can select each one and see the difference. So there's a wide variety of applied calculation things one can do. So if I go to the, just to cover this off, if you go to the manual where I removed the modifier for contact correction, if you look at the residuals of that, it's random. But what's very interesting, if you want to see how the contact correction works, if you remove time and basically show all the data points and calculate, you can see the effects of adding that data, those points back in. So now that I'm showing all the data, you can see where the heat is penetrating through a layer of contact resistance, and as the heat diffuses into the sample, that region of the temperature rise is linear, and the heat is diffusing without the effects of contact resistance. So you can manually remove that based off visual observation. This is a key advantage of the MP1 transient plane source method, is that you don't have to do this. If you want to manually do this, to iteratively see the effects of contact resistance and the calculation, you can of course do that, but you don't have to. That's why we've enabled and created this capability of applying that contact correction, so you don't have to. And when you look at the individual results, so this is a summary of all the results for conductivity, diffusivity, and specific heat. And then you have the mean averages of each of those columns. If you select on an individual row, it shows the calculation parameters or modifiers used, as well as quality indicators. So again, if you remember the quality indicators for temperature rise, the TCT should be above 0.3. Probing depth, in this case, 0.3 represents the radius of the selected sensor, which is 6.4. So the probing depth is certainly deeper than 6.4 millimeters. The resultant penetration depth is 8.6 millimeters. And this is telling you the linearity of the residuals. So if you look at those residuals, it's very tight. We're into the microkelvin of linearity. You can see that RMS is green, it's acceptable. So if these were not acceptable or outside of ranges, you would see these change colors, and it would give you, if you mouse over it, would give you advice on how to change those. Here's the individual same results for that one particular experiment, as well as the contact correction. So you actually get, when you apply that contact correction, you get the heat capacity, the capacitance, the conductance rather, and the contact resistance between the sensor and sample. And that's key. So if you select all of these, you can save as, so you can save the new calculations you've done with that data, which we'll do. You can replace it, as well as you can generate a report. So if we generate a report, we'll just leave it as test data in Excel and click Save. And it will save it and automatically open up your Excel of your data. So here's our summary of our Excel data. Your user ID, your paths of saved data, which batches, and in a number of columns representing the parameters, your average of your data, as well as your summary and your contact correction if applied. And then you have your second batch, and if you had any notes associated. That's essentially the pretty basic description of making a measurement, scheduling a measurement, and opening that data up in the analysis module. For further information, we'll be exploring several of these individual areas of technical nature in our quick start guides, as well as other videos. Thank you.